Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss Planck's law of blackbody radiation and its derivation. Let's begin. Before Max Planck, the scientist, a German physicist, before him, the scientists named as Wenz, Stephen and Boltzmann, Rayleigh and Jaynes proposed their laws regarding blackbody radiations. What be the spectrum of particular blackbody radiations? But they can't explain the blackbody radiation spectrum by using classical mechanics. Means the experimental result of that blackbody radiation doesn't match with their theoretical result. To avoid such type of difficulties, Max Planck proposed his laws, or we can say proposed his hypothesis regarding blackbody radiation of spectrum. The classical theory could not explain what be the distribution of energy in the spectrum of a blackbody. In order to avoid such difficulties, Max Planck, a German theoretical physicist, made an important hypothesis which is known as Planck's hypothesis. What are the hypotheses proposed by Max Planck? Number 1, a blackbody radiation cavity. Blackbody radiation cavity means a cavity where blackbody radiation performed. That cavity is filled of not only with radiation but also with simple harmonic oscillators, and that simple harmonic oscillators also called as resonators. Okay. The first assumption or first hypothesis proposed by Max Planck, the blackbody radiation cavity is filled up with not only radiation but also simple harmonic oscillators. Since simple harmonic oscillators, so the exchange the energy of radiation. So what be the energy? The exchange of radiation energy with matter does not take place continuously but discontinuously and discretely, which is an integral multiple of small amount of energy is called the quantum or photon. What did it say? In previous theories as proposed classically by various scientists to explain the phenomenon of blackbody radiation spectrum, they assumed that the energy is continuous. But here, according to his hypothesis, he indicates that energy is not continuous but it is discontinuous and is discrete in nature. Since it is discrete, so what be the energy? That energy is the integral multiple of a small amount of energy which is called quantum or photon. Mathematically its value, a photon of energy is equal to s nu, where s be the Planck's constant and nu be the frequency of that particular radiation. The constant as Planck's constant according to Max Planck, and its value is equal to 6.62 into 10 to the power minus 34 joule into second, whereas nu be the frequency. By using these two hypotheses proposed by scientist Max Planck, he explained the blackbody radiation spectrum. Now we mathematically derive the expression by using the hypothesis proposed by Max Planck. As we say, the blackbody radiation cavity is filled up not only with radiation but also with simple harmonic oscillator, which is called resonators. Suppose in that blackbody cavity there are N0, N1, N2, N3 up to Nn number of Planck's oscillators. Planck's oscillators, or which are called resonators, having energies in its second hypothesis, that energy is the integral multiple of small amount of energy, which is called quantum or photon of energy. Let N0 number of such Planck's oscillator having that energy integral multiple, let 0. N1 number of such Planck's oscillator having the energy, let h nu. Similarly, N2 numbers integral multiple 2s nu, 3s nu. Nn number of such oscillators having that of energy ns nu respectively. Therefore, the total number of such Planck's oscillator, total number of Planck's oscillator, that is, let n is equal to n0 plus n1 plus n2 plus n3 up to nn, that equation number 1. And the total energy possessed by this Planck's oscillator and total energy is equal to energy of such oscillators, n0 number of oscillators having energy 0, n1 number of oscillators having energy s nu, like this. 0 plus s nu plus 2s nu plus 3s nu up to nh nu, the equation number 2. Now we have to calculate what be the number of such Planck's oscillators and the total energy. To calculating that number of Planck's oscillators, we can use Maxwell's distribution law. According to Maxwell's distribution law, the total number of Planck's oscillator, the total number of Planck's oscillators n is equal to n0 into e to the power minus ns nu divided by kBt, whereas kb, that is the Boltzmann's constant. According to Maxwell distribution. Now we can put, that is Nn, where small n stands for n is equal to 0, 1, 2, 3, like this, where small n 0, 1, 2, like this. Therefore, equation 1 will be n is equal to, for n0, n is equal to 0, n0 plus n1 when n is equal to 1, that is n0 into e to the power minus h nu divided by kBt, plus when n is equal to 2, that is n0 e to the power minus 2h nu divided by kBt, up to putting that small n as n, that is n0 into e to the power minus nh nu divided by kBt. Here we can take n0 as common, inside that of bracket 1 plus e to the power minus h nu divided by kBt plus e to the power minus 2h nu divided by kBt, up to e to the power minus nh nu divided by kBt. As we know, the expression for 1 plus x plus x square plus x cube up to x to the power n is equal to 1 divided by 1 minus x, that is the series expansion of 1 divided by 1 minus x. Similarly, here in place of x we write e to the power minus h nu divided by kBt. Therefore, the expression for n is equal to n0 into its expansion as 1 divided by 1 minus x as e to the power minus h nu divided by kBt. Or n is equal to n0 divided by 1 minus e to the power minus h nu divided by kBt. That is equation number 3. Here the total number of such Planck's oscillator is calculated. Now we can calculate what will be the total energy of such oscillators. Similarly, that equation 2 can be written as Similarly, equation 2 will be, what is equation 2? That for total energy expression we can write it as total energy expression E is equal to first term as N0 into 0 plus second term as H nu into N0 e to the power minus H nu divided by kBT plus 2H nu N0 e to the power minus 2H nu divided by kBT plus up to NH nu N0 into e to the power minus NH nu divided by kBT, or E is equal to that term as entirely 0. In these terms we have to consider the common term as N0 into H nu, N0 into H nu into e to the power minus H nu by kBT. We take common. So inside that a bracket it will be 1 plus here 2 into e to the power minus H nu divided by kBT, as we prefer e to the power minus H nu by kBT as common. So in that term it will be e to the power minus H nu by kBT. So in that of bracket we obtain e to the power minus H nu by kBT plus up to continued n into e to the power here n minus 1 H nu divided by kBT. As we know that the series expansion 1 plus 2x plus 3x square up to n x to the power n minus 1 is equal to 1 divided by 1 minus x whole square. That formula is used here. The energy is equal to n naught H nu e to the power minus H nu by kBT into this expansion as 1 divided by 1 minus e to the power minus H nu by kBT, that is for x H nu by kBT whole square, or E is equal to N0 H nu e to the power minus H nu by kBT divided by 1 minus e to the power minus H nu by kBT whole square. That equation number 4. Now we calculated total number of such Planck's oscillator and total energy possessed by this Planck's oscillator. Then the average energy per Planck's oscillator, the average energy per Planck's oscillator E average is equal to total energy divided by total number of such Planck's oscillator. Therefore, E average is equal to total energy, that is n naught h nu e to the power minus h nu divided by kBT whole divided by 1 minus e to the power minus h nu divided by kBT whole square whole divided by number of Planck's oscillator, that is n0 divided by 1 minus e to the power minus h nu divided by kBT is equal to E average. n0 cancelled out, and 1 minus h nu divided by kBT whole square. Here 1 minus h nu divided by kBT cancelled out, only one term exists. So finally we obtain h nu into e to the power minus h nu divided by kBT whole divided by 1 minus e to the power minus h nu divided by kBT is equal to E bar. Now in that of numerator side and denominator side we divide e to the power minus h nu by kBT. Therefore in that of numerator we have h nu divided by, here 1 divided by that term, it will be e to the power h nu divided by kBT minus this term divided by this term, that is 1. So the average energy is calculated. Now we have to formulate the Planck's radiation law. The radiation spectrum means the energy density belonging to a particular frequency range to be calculated. To calculate that one, first we have to calculate what be the number of resonators per unit volume in a particular frequency range. From Rayleigh and Jeans law, the number of such Planck's oscillator in the frequency range nu and nu plus d nu. In that frequency range, what will be the number of such Planck's oscillator? That is n is equal to, as we calculated in case of Rayleigh-Jeans law, the number of mode of vibrations, means what will be the number of allowed frequency range. Here we calculate the number of such Planck's oscillator in that given frequency range. We already derived that expression in case of Rayleigh-Jeans law, that one is 8 pi nu square divided by CQ d nu. Therefore the energy density of blackbody radiation in the frequency range nu and nu plus d nu is u nu d nu, energy density in that of frequency range, and it's the number of Planck's oscillator in that of frequency range into the average energy of a Planck's oscillator, that is 8 pi nu square CQ d nu into average energy h nu divided by e to the power h nu by kBT minus 1. So u nu d nu energy density of that black body radiation in that of given frequency range is equal to that one, that is 8 pi nu square d nu divided by CQ into h nu divided by e to the power h nu by kBT minus 1. That one is nothing but Planck's law of black body radiation in terms of frequency. This is the expression for Planck's law of black body radiation in terms of frequency. Planck's law of black body radiation in terms of frequency. Again, in terms of wavelength, we know that nu is equal to c by lambda. Therefore, d nu is equal to minus c by lambda square d lambda. Here we have to consider the magnitude term. Therefore, let me take it as equation number 6. Equation 6 will be u lambda d lambda, energy density in that of wavelength range lambda to lambda plus d lambda is equal to, that is 8 pi in place of nu, 8 pi h CQ c by lambda whole square into 1 divided by e to the power h c by lambda kBT minus 1 into minus c by lambda square d lambda. Here only we prefer that magnitude term. Therefore, u lambda d lambda is equal to 8 pi SC divided by lambda to the power 5th 1 divided by e to the power SC divided by lambda kBT minus 1 into d lambda. This is the expression for Planck's law of black body radiation in terms of wavelength. This is the expression for the Planck's law of black body radiation in terms of wavelength. And that theoretical result for that of energy density of black body radiation spectrum is exactly equal to that of experimental data. So, here with the help of this video lecture we understand the concept of Planck's law of black body radiation, the hypothesis proposed by Max Planck. By using that two hypotheses we derive total number of such Planck's oscillator, then total energy possessed by this Planck's oscillator and the average energy for Planck's oscillator. Next, the energy density of blackbody radiation in a given frequency range, that is the number of such Planck's oscillator in that of given frequency range into the average energy for Planck's oscillator. This is the expression for Planck's law of blackbody radiation in terms of frequency. Then expression for Planck's law of blackbody radiation in terms of wavelength. So, with this useful and informative notes, let me wind up the session. Thank you.